approximately follow a normal distribution which can be normalized or can be standardized. The x bar minus mu divided by square root of n. They'll follow the real square, right? Like this. And then to do the multiplication can be doing like this. We multiply n both on the denominator and also in the numerator. So summation n, that is the summation x, right? The n times mu is mu. The n times s bar is equal summation then the sigma, so this is so I'm going to cancel square root of the n. This is the sigma. Alright, yes. Okay, from the central limit theory, we know that regardless of the distribution of the population, the distribution summation xi is a possible normal distribution with n mu and the variance n variance of the n sigma squared, right? As long as the sample size is so large and the sample limit theory will apply.都不一样。有没有记龙水？几点啊？说话，一点跟我一样啊，我还讲话嘞。一点，你住哪里？大子是租的吗？还是你自己家住哪里？住家里，那你怎么来？搭捷运？哦，那还好啊，捷运你不用开捷运啊。对，那是 OK。那你在虚弱什么？人家都已经吃2碗了。那你到底在搞什么那么虚弱啊？瘦成这样，人家2拳你就倒了，不行这样。一拳，碰一下就倒了。哎，真的是。Then, so it won't matter. So this will be following the normal distribution with the mean and mu. So you can find here, right here, it can be clearly seen. So this is a statistic. Subtract is the mean, divide by is the standard deviation. So this, the mean of the summation xi is going to be m mu. Its standard deviation is sigma square root of n. So its variance going to be the n sigma squared. It's n mu and sigma squared. That's why I write in different form. And therefore, regardless of distribution, the sampling distribution of the sample mean is approximately like this one. This is sampling distribution. It won't matter the original probability distribution is, as long as the n is really large. Okay. So the chi-square distribution, okay, there's an important thing. The chi-square distribution is defined as if the x1, x2 to xn are normally independently distributed random variable with a zero mean and the univariance, then the random variable x1 squared, x2 squared, xn squared for each one. Okay, this definition, very important problem for each one are normal distribution NID 0 universe. Z1 is a random variable from standard normal distribution. Z2 until Zn are all from the standard normal distribution. Then we square them up and sum them up. You will follow a chi-square distribution. How many degrees of freedom it has? 1, 2, 3. The number of the z square. We have an nz squared, so the degree of freedom is equal to that. Degrees of freedom. So distribution is a little bit skewed. Skewed means that it's a 12, the right skew. You can see that the tail is extenuate to the right. There's a mean and the variance is 2n. The table of the percentage point or percentage score of the chi-square distribution is given appendix table 3 on the back. It's on the back of the textbook. Then another useful sampling distribution is called a t-distribution. T-distribution. It is standard normal random variable. If x is standard normal random variable, and if y is a chi-square random variable with k degrees of freedom, then f. If the x and r are independent, then random variable is defined as a t-distribution. Let me show you why this is true. So we look at the definition of the t. Okay, x is standard normal. Standard normal random variable, y is a chi-square distribution with a degree of freedom of n. And x and y are independent each other. So t distribution is defined as an x. Okay, I will say z. And the chi-square distribution n divided by is a degree of freedom. K degree of freedom, for example, like this. And the z and chi-square are independent each other. So, in this case, so what the z is minus. Yeah, let me see that. Yeah, am I right? The x bar minus mu divided by standard deviation, that's z, right? Am I right? Something. Do you conquer? I think you did, right? Divide by the chi-square distribution. So this is a chi-square distribution. So the M1 times S squared divided by sigma squared. So we will follow a chi-square distribution of the degree of freedom of n minus 1. Right? Since the n minus 1 s squared divided by that is equal to the summation xi minus x bar squared and divided by sigma squared. So that is equal to the xi minus x bar divided by sigma squared summation I starting 1 to n. So totally we have a degree of freedom of n minus 1. Then can do the cancellation. So put a little bit trick. Yeah, no. This is a very complicated bar. Minus mu divided by sigma square over n. And times to do the so this is S and the sigma. Alright? So finally turn out to the x bar minus mu and the S divided by square root of n. We'll follow the T distribution with the degree of freedom. Where does the degree of freedom come from? The freedom and then degree of freedom.这我统计课有讲过啊。有吧？
那个是另外一个，
什么？
是陈子立老师的。
陈子立有教吗？
有啊。
这样是 n 还是 n 减一？
嗯。啊呀呀 ，m s
没错没错。
我就觉得怪怪的。
那整个式子都有导给你们看，应该有。
啊？
嗯？没有。陈子怡老师没有导。
只是说是
一例两例。
什么一例两例？
吃力。
我要跟他讲。注意了，下次聚餐他就坐你旁边。OK。一例两例，搞错，将来就是。Then the last sampling distribution, based on normal process, we will consider is called the F distribution. The F is chi-squared divided by is a degree of freedom. Chi-squared 2 divided by is a degree of freedom. Hello guys. it defined as a ratio of the two chi-square distribution divided by its degree of freedom and take the ratio. Like W and Y are two independent chi-square random variables, and mu and nu are degrees of freedom respectively. Then the ratio, the F, has two degree of freedoms. The numerator degree of freedom df1, the denominator degrees of freedom df2. So, yeah, this sounds shady. Okay, sample from the Bernoulli. Bernoulli is a single observation. No, the single observation of a Bernoulli experiment, and so the outcome will be dichotomous, either 1 or 0. So suppose that the random sample of m observations, say x1 to xn, is taken from Bernoulli. So sum of them will be a binomial distribution. Like we take it, we sample it with replacement. So furthermore, there's going to be the binomial distribution. Poisson process. The Poisson process is a case of the counting process. How many points, how many events, or how many failures occur in a fixed interval of time. The Poisson process was introduced in the previous section, consider random sample. So, yeah, this is some sampling distribution. So distribution like this, x equal to x1 to xn, is also a Poisson process of the parameter n lambda. So more typically, the sum of independent Poisson random variable distributed with the parameter equal to the sum of the individual. So summation xi divided by n, this is 1 over n. So mu x bar going to be the lambda, mu x bar going to lambda divided by n. Since a Poisson distribution, it is a quite special. It's a mean equals to its variance. That's why we have a lambda divided by n. So 4.2. Point estimation of the process parameter. So distributions are described by their parameters. Well, parameters are generally unknown, not as a priori, actually not. So must be estimated. So we have two different classes or two different categories, point estimation and the interval estimation. So point estimator is a statistic that is a single numerical value, like x1 plus 2, x2 until xn divided by n. We also can use a different estimator like x1 plus x3 plus x5 divided by 3. So have we introduced this comparison last week? Did we? Yeah, there's a boy from 大直. Hello. 你在睡啊？干嘛？你到底干嘛？来，你自己出去走一走，去洗把脸去吧。1点钟睡，你真的不行，你就9点钟睡啊。没本事你就9点钟睡啊。
差不多，9点到现在。
Okay, parameters are general unknown but we estimate. So point estimate is a statistic that's single numerical, so value. So the first one, the point estimator should be unbiased. What is the meaning of unbiased, gentlemen? 你手永远放那边，永远都不记没关系啦。我告诉你，写了一大堆，你就在那边看头。There's a monkey show on the stage 。什么都不管啊，老师表演今天还可以。Keep going， 来，第一个 ，the point estimate should be unbiased. What is the meaning of the unbiasedness？
不偏。
什么意思啊 ？What？ 什么相减？什么跟什么相减？ Hello. Yeah, more, yeah, more or less, more or less. So unbiased, I mean, this is parameter estimate. Theta. We put the theta is unknown parameter. We put the caret symbol on the top, indicating the point estimator. So if the expected value of the point estimator equal to the unknown parameter itself, then it is unbiasedness. For example, expectation of x bar equal to this unknown parameter. So bingo, it is unknown. So it is unbiased. It's unbiased estimator. Bingo. Yeah, let me say it again. Then how about that? I would like to use the theta one is equal to the 2x1 plus the 4x2 plus f3 divided by 7. Is this unbiased estimator, gentlemen? Theta 1 half. Is that an unbiased estimator for me? Is that it? Yes, of course. Two more plus 4 more plus more 4, 6, 7. Yeah, bingo. We are so lucky. Yeah. Unbiased. Yeah, bingo. Can we do that? Yes, we do. Yeah, we can do that. Then, what is the bias estimator? No. No, it is the bias. So, yeah, of course, this is the bias. No, it's bias. Okay, this is the first property of the unbiasedness. Second, the point estimator should have a minimum variance. And any parameter point estimator is a random variable, then a minimum variance point estimator should have a variance that is smaller than the other, the variance of the other point estimator of that parameter. So that is called the blue, B-L-U-E. shift the blue. The best on the lead on by zero. So compare. So compare this one. Compare this one. This is equal to the what? This one, and compare to this one. Compare to this one. No, this is bias, so it can be considered. Compare to this and compare to that. It's equal to the x bar. X bar and theta 1 net. Which one is better? Yeah, which one is better? We wish we achieved the minimum variance estimator. So we compare the variance. So what is the variance of this one? Yeah, the girl from Qiaoguang, right? Lindong or from Qiaoguang, right? Yes. What is the variance of that? So what is that? You don't know. Do you read the book? Then, and what? Somebody? You. The variance of x bar. Square over n. I mentioned this over 100 times. If you still don't know this quite elementary question, you should not be here. You should not be here. If you don't know anything about that, you should not be here. This is so basic. Why are you wasting time in the class? Hey guys. This is a very serious question. Okay. What about this? Okay. And Miss Zhao. Seven out of the operator. This is 49, right? 7. 7 by 7. Right, take it squared up, and this is 4 sigma squared plus 16 sigma squared plus sigma squared. How many? This is 20. And then you do that. That's sigma squared. 49 divided by how many? 21, right? Yes, it's about it's about 2.3, am I right? compared to that sigma square, compare the point estimate this and the point estimate this. Which one is better? This shot. This shot. If n is greater than or equal to 3, then x bar will be a better point estimator. Otherwise, right? Compare the variance. See that? See that? Typically, sample size greater than 5. So, x bar always unbiased and the minimum variance. Unbiased and the minimum variance point estimator. Alrighty. So the sample mean here, the sample mean and variance are unbiased estimate of the population mean and the variance mean sigma respectively, like we have here. And however, sample standard deviation not a unbiased estimate. This is a different idea. Let me say it again. The sample standard deviation is not an unbiased estimator of the sample standard deviation. S squared going to be unbiased estimator for sigma squared, no problem. Let me say it again. S squared is an unbiased estimator for sigma squared, no problem. However, the S will not be the unbiased estimator for the sigma. Totally different. So on the contrary, in the later, so we're going to use S divided by C4 as a, so to obtain that the C4 is a coefficient, and this is the value, give the value of C4 for sample size between 2 and 25. We can obtain an unbiased estimator of standard deviation based upon that. S divided by C4. So later. Where can we get this value of C4 from the lookup table on the back? Where the R bar divided by D2. The D2 also is available from the back of the table. On the back of the table of the table. So in many applications, so turn to the page 110. In many applications of statistics to quality and process improvement problems. So it is so convenient to estimate standard deviation by range, x1, x2 to xn. What is the definition of the range? So what is the range? RANGE. Range. What? The max, the difference between max and minimum. Within a sample. Let me say it again. Within a sample. The difference between the max and the. So the range of sample is the definition between within a sample max minus minimum. So R is simply the difference between the largest smallest value sample of observation, then the random variable W equal to R divided by sigma is defined as a relative range. scale with respect to the space. Then, so distribution of W has been well studied by the statistician. The mean of the W is considered a D2 that depends on the size of the sample size. And depends on the sample size. So therefore, the unbiased estimator of the standard deviation sigma of a normal distribution can be defined as that. So, alright. So this is R bar divided by D2. So the sigma head. So therefore, unbiased estimator of standard deviation of the normal distribution can be defined by R bar divided by D2. So which is going to be used in the statistical process control. Yeah, would you turn back to the back of the textbook to find the table for D2？ 让我们看一下有没有 D2 的表格，快点。你看，你不带书你怎么看表格？谁没带书举手？快点！谁没带书举手？举高点！全班就你，你最厉害。我不要知道他名字，否则他绝对不会过的。我告诉你，我就是不希望知道每个人真的名字。我全班我只知道2题，其他我都不知道，因为他是我 IG 的好友。怎样？有意见吗？没有。
哎呦，
老师我没有对啊。对啊，老师我有追踪你。
对啊，
我有追踪
你们又不跟我说话，你要打字啊！我怎么知道你是谁？我是白头翁，我是老鹰，我是老鼠，你要打字啊！
没有问题。
我看你。
我会发了你的题目。
不要发了我。
我会跟你的，我会问你。
哪里啊？
记住啊，记住啊，两个人讲下来 ，A 一个 A12，用光笔把画成，快点。我们看到，用光笔把画成。
对啊，我确定一下。
So the values of D2 for sample sizes between 2 and 25 are given in the context table. Can we find that? Ready? Yes. Can we find that? Okay, relative efficiency of the range. Sample size relative efficiency 1.0. 3, the 0.992, and so on. So this that value. So the relative efficiency. So how can we do that? D2 seems when we get the R bar, then there's a D2. We cannot get the value of the D2, so this is sigma. So we do the simulation. How the values are estimated from simulation. So we generate the data or observation from normal distribution. Then we take the sample and calculate the range. We calculate the range. Then to compare with its standard deviation, then like this, I would like to say that. Or then the D2 can be obtained. We perform 100 or 1,000 or even hundred of thousand or even a million so many times that we can get a conversion value or an asymptotic value of the D2. So from moderate value n greater than 10, the range loses efficiency rapidly, so that need to divide by a smaller value. So when we get that D2, so since it is underestimate, the R is an estimator for the standard deviation, so it needs to be adjusted. So we need so the R should be inflated to be an advanced estimator for standard deviation. So relative efficiency decreases when sample size increases. So for small sample size, say n less than or equal to 2, it works very well. Yeah, 0.99297, yeah, it's pretty good. It's entirely satisfactory, so the R is quite close to an unbiased estimator for sigma. However, we use the range method to estimate standard deviation for a certain type of the control chart. Chapter 6 will be addressed later. So supplementary test material, we'll talk about that. And 4.3. So there's an important formula you always need to bear in mind on the text in the page 110, equation 4.19 and 4.20. 公式4至19跟4至28画起来，第4章啊，4至19、28。Equation 4.19 and 4.20. Okay, move to the 4.3. Page 111. Statistical inference for single sample. So statistical inference, we make a decision. So we do the prediction. So compared to the machine learning, we have is quite trendy topic in the current era. What is the comparison between statistics and the machine learning? Okay, so we'll break.